Hi, and welcome to another one of my videos. Today I'll be continuing my previous discussions about the atmosphere, temperature in the atmosphere, how we can actually say that we need gravity in order to have the effect we see with weather balloons and all that sort of things. So in order to do that, I will go through the following. First, I'll talk a little bit about the metric system, because that is actually essential to what physicists do and to understand this subject in detail. Then I will go briefly over the ideal gas law. I've done that before, but I will put a little more detail on it. Then I will go to the subject of buoyancy. And then finally I will discuss the atmosphere. I think that generally this is sort of a general statement from flat earth believers that we can have buoyancy without gravity, or we don't need gravity. And the atmosphere is specifically to a video about by Brian Mullen about the temperature variations in the atmosphere. I would like to go a little bit into details about the layering of the atmosphere and actually how we can say, how we can understand and make it plausible that these temperature variations exist in the atmosphere. Alright? The metric system basically is comprised of three fundamental units. It is a length unit, which we have in meters, and there's a time unit, which we have in seconds, and then there's a mass unit that we have in kilograms, and kilograms is abbreviated kilograms, but seconds is abbreviated S, and meters is abbreviated M. So from that we can sort of derive some new values. For example, we can derive speed. The speed would be meter per second. Now in physics, it is usually it's the standard to write the speed or something like that in this form. This is the equivalent of writing meters per second. It's the same. Alright? Just so we're on the same page. Acceleration, I will just write it like this, is how much the speed changes per second. So that would be meters per second, or meters per second squared. Then we can derive force, which is in newtons. And so a newton is defined, we can look at, if we look at the formula, F equals ma. Alright, so mass, we have that's in kilograms. And we have the acceleration here, so that is meters second squared, or per second squared. So that's the force. And from here we can also derive pressure. It's in the unit of Pascal. And so pressure is sort of the force per unit volume. And so we haven't defined the volume yet, but let's do that quickly. A volume. So let's first define, we need a volume here. Pressure. The pressure is the force per area. Yeah. So what can we do? Alright, so let's first define the area. The area, or derive it, is length times length. So that is meter squared. The volume, we can say that is sort of area per length. So that would be meters cubed. So now we can look at the density, the pressure. So that would be the force, that is kilograms per meters per second squared. And then we need to say that is the force per area, so that is per meter squared. And we can rearrange that to give us kilograms per meter per second squared. So this is some of the basic units that we can derive from the metric system alone. One of the units that we will be using here is mass density. This is very important. So we say that mass density is defined as mass per volume. Well, we already have the mass, that's kilogram. We also define the volume, that is meters cubed. So we actually gonna write this as kilograms per meters cubed, or meter to the minus third. Alright. So these are some of the basic units that we're going to use from now on. Now, of course, because I have a relatively small whiteboard, I'm going to erase that, and then I'm going to continue with the ideal or perfect gas law. You can use both names. So, let's define the ideal gas law. Now, for chemists, or the most usual way to express the ideal gas law is in this form: PV equals M times R times T. Now, let's define the values here. Sorry, I need to do like this. Let's call it R hat. We're going to use that. So, P is the pressure, V is the volume, N is the number of moles, R is the universal gas law, the universal gas constant, and T is the temperature. Now, we could also define this in another way. We're not going to use it, but we could do that as well. By substituting some of the values, we could get N, K, T. These are the same. This is the Boltzmann constant, and this is the number of particles. So instead of working, sometimes for physicists, it's easier to work with the number of particles, because we would then just have a number to count, instead of number of moles, because then you always have to convert. We're not going to use that, so I'm going to erase it again. What we are going to use is another form of this formula. This is the form that is usually used in meteorology and climate physics. We define the mass density as the number of moles times the mass divided by the volume. Volume. And we also introduce the specific gas constant, and you can see that when I write the formula up, because if we substitute this in, we get pressure is equal to the mass density times the specific gas constant times the temperature. And the temperature in both cases are in Kelvin. But there's an easily, we can just say that temperature in Kelvin is equal to the temperature in Celsius plus 273.1. It's a relatively easy conversion. Alright, so what can we say here? Well, first we need to define what the specific gas constant is. So the specific gas constant is equal to the universal gas constant divided by the mass. So we can say that the molecular mass. So we know that the molecular mass of air is equal to 29, the average. And we know that the universal gas constant is equal to 8,314. So we can quickly calculate, I'm going to erase that and put it down here, but we can quickly calculate that the specific gas constant for air is equal to 8,314 divided by 29, and that gives us 287 joules per kilogram per Kelvin. This is J. We need that further on. Alright, I'm going to erase this here. We have that down here. So let us take a specific example. I think that the temperature in this room is roughly about 25 degrees Celsius. And so let's put that up. Temperature of this room, I'll just call it room, is equal to 25 degrees Celsius, and that is 298 Kelvin. I think that is normal room temperature. And the density of air is equal to 1.2 kilogram per meter cube. So let's calculate what the pressure would be inside this room. The pressure in this room would be 1.2 times the density, sorry, not the density, the gas constant for air, that is 287, the temperature times the temperature, 298 Kelvin, and that is 102,631 Pascal. Now we can convert that to hectopascal or millibar, that is roughly 1026.3 millibar or hectopascal, or we can further convert it because we know that millibar is mil is per thousand, so we have that in this room it is roughly 1 bar pressure. And I think that sounds quite reasonable. That's what humans like. Yeah. So this is the ideal gas law. Some other things that we need to consider just quickly. I'm going to erase this again. Let's imagine we have a box with a piston where there is a gas inside that gives a pressure on the piston. The gas has a temperature, and we know that if we increase the temperature, the pressure increases. So there's a we have that from the ideal gas law. If I increase the temperature and these two are constant and the volume is constant, because it is constant, then the pressure will also increase. So let's look at it in a different way. And I'm going to take this from my book here. I actually had to look it up. Thermal Physics by Daniel Schroeder. And basically what we can say is that we can define we can redefine this formula as saying, well, let's assume that we have a particle in here that moves around with a velocity v. And we can from that calculate that the ideal gas law, if we rewrite it to PV equals kt, that it can also be written as PV equals mv squared. It's a bit the average. This is the average of all the particles. So this is the average kinetic energy of all the particles. But this means that if we add the ideal gas law to this, we can actually get that the temperature is equivalent to the average kinetic energy, or that there is a relation between the temperature in the box and the velocity. So this means we can solve for the velocity. We can quickly do that. It should be something like v squared equals kt over m, and then because we have a square, it is the square root. So you can see here, this is just a quick definition, that if I increase the temperature and keep the Boltzmann constant, that's constant, and the mass should also be constant, I'm not going to change the particles in there. If I only increase the temperature, then the velocity will also increase. So there's a connection between the velocity of a particle and its temperature. And this is important to understand why we can say that the upper atmosphere, if we put a thermometer in the upper atmosphere, the thermosphere, it would say nothing. Because what does a thermometer do? Well, a thermometer, the measuring end, this is the measure end, actually measures the temperature, which is also the kinetic velocity, the velocity of the particle, or the kinetic energy. So when a particle, let's just take an air particle, hits the thermometer, it transfers some energy to the thermometer and moves it away again. Now, it's not enough to just measure one particle. We need to measure a lot of particles. Sorry. So what a thermometer do if you hold it out in the air is that it measures the average kinetic energy of all the particles which we have here. This is the average kinetic energy. So it's sort of an average measurement of the average temperature of all the particles in the room. And that's because all the particles in the room does not have the same temperature or the same kinetic energy. You can put it like this and say that if we have the temperature up like this, we have the temperature here, and then we have the number here, then it would be something like this, where the middle value would be, well, in this room it would be 298 Kelvin, something like that. But we can also have particles out here which is probably 400 Kelvin maybe, and we can have particles here that are perhaps 100 Kelvin. But the average, most of the particles in the room, and when we measure the average value of them all, is 298 Kelvin. Alright, so I want you to remember this when I'm going to the final part of this video to talk about the atmosphere and the temperature variations in the atmosphere. Alright, Next I will introduce buoyancy and try to explain why we need gravity in order for that to work. Okay. In order to understand what the buoyancy force is, we need to define it. I want to define buoyancy force as the pressure force on an object expanded or put in a liquid and present in a gravitational or gravity field. So we need gravity. Why is that? So let's take a simple example. We have a tub or a swimming pool, and we take a big air ball or bathing ball, I'm not sure what you call it, and put it in the water. And if we just put it there, then it will float on top of the water. And if we try to push it down, we will feel resistance. And in order to understand any of this, we need to know why this is. And the answer is that the buoyancy force only works because pressure increase with or because of gravity. Now let's rephrase it. Due to gravity. So why is that? And how can we sort of theorize it? How can we explain it? How can we, well, make it plausible that it is so? Let's imagine that we had a piece of water or a piece of air, anything floating outside in space, and that we could have it so that the water wouldn't dissipate out in space. It would be confined by itself. So what would we need to confine it? We would need a force. But how would we do that? Well, we could put something around it. I just said that that's not the case here, but we could put something around it to stop it. Let's say we had a ball of water with a corkscrew, a big corkscrew on it. Then the water would try to expand out because it wants to obtain equilibrium. We have an area with a very high density of water, and we have the surrounding an environment with a very low density of water, and then the water would try to equalize so the density of water would be the same everywhere. But if we put something around it, then we would have a force pushing down on the water. If we remove that, the water would dissipate out in space. So let's just think about this for a second. Here we have Earth. Let's try to forget the water for a second and think about the atmosphere instead. So here's the atmosphere. It's actually, this is grossly exaggerated, but I think it works. It explains it very well. So we have rays coming from the sun out here, energy that heats up the atmosphere. And as I've just shown you, the atmosphere, a particle, when it is heated up, it also gains velocity. And the thing is that we can calculate the escape velocity from Earth. But in order to do that, we need some force that is not dependent on buoyancy or anything else. Because the buoyancy is dependent on pressure, and pressure is dependent on, if not gravity, at least some kind of force that increase pressure. Let's expand this bowl of water here and say we know that this is pure water. Let's just say there are no other particles in there, it's just pure water. We know that if we measure, let's say we measure the pressure here, it's equal to 2 bar, and we measure it down here, it's equal to 4 bar. And why is that? Well, it's because a force of gravity, some force, I will retain that it's gravity, some force is pulling down on all the particles. And it is evident that there are more particles pushing down on anything here than there are here, because there are more particles in this area than there are in this area here. It's a smaller area, less particles to push. And if I expanded the top further, the pressure would increase because there are more particles to push down on it. More particles to push down, but we need a force. And again, it can't be buoyancy because it is dependent on that force. Buoyancy is dependent on that force. Because otherwise we would have that air out here, just say P water, P air, is equal to 1 bar. If there were no force pulling down, even if we had the air here, it has a pressure of 1 bar. That's because all the particles up onto the upper atmosphere, the edge of the atmosphere, it's no solid edge, but the edge of the atmosphere, all of them is weighing or pushing down on all the other particles, and they are pushing on us from all directions with a pressure of 1 bar. Alright, so if we remove gravity, just like that, what would happen? Well, the sun would heat up all these particles in here, and since there's no escape velocity, well, at some point they would begin to fly away. So how does that happen? Well, we have a lot of particles in here, right, in the atmosphere, and they bounce into one another, and at some point some particle get to the edge of the atmosphere and escapes out. And since there's no particles out there to reflect it back because of collisions, it would escape out, and Earth would have no atmosphere. All right, and we can't really employ density here, because density compared to what, right? Because, well, we could use density, but it wouldn't really make sense, because if density is the force pushing down, then, well, that won't make sense. So that's the statement. We need some force to create pressure. All right. And that gives us the explanation for this. Erase that earth here. That because gravity increased the pressure on the water, it's also because of the density of water, right? But it's also because of gravity that the density, that the pressure of water can increase with depth. and that the pressure in the atmosphere can increase with depth. You can actually model the atmosphere as a fluid. That means that the pressure pushing down from air is less than the pressure pushing up from the water. Alright. So let's expand that a little bit further. Let's employ or use Archimedes Law, or some variation of Archimedes Law. We can define that as the density times the volume and times gravity. And so if we define this as the mass, because it is the mass, then we have weight, because F is equal to ma, and that is in Newton, right? The force. And so we actually have that weight is actually defined as newtons. Alright. So Archimedes' law says that by putting something down in water, for example, and then calculating, having the density and the volume and the gravitational force, we can find the weight. That is, we just need this formula actually. Alright. So let's take an example. Let's say that I have some blob or parcel of air. Let's say that I could define this area as my parcel. Then I could say that, well, this parcel would have a pressure, it would have a mass density, and it would have a temperature. There would also be the environment. It will also have a pressure, it will also have a mass density, and it would also have a temperature. Now, at this moment, I can safely say or assume that the pressure of the environment is equal to the pressure of the parcel, and let's just say that this is 80,000 Pascal. Now, why can I do that? I can do that because if this pressure wasn't equal to this pressure, this parcel would just instantly expand. You can take a simple example, take a balloon, blow it out, put air in it, and then stick a needle, and at the instant that the rubber around the air, which creates pressure or force to keep the air at a higher pressure, as soon as that disappears, the balloon will, or the air inside the balloon will expand. Actually so much that it gives a sound. That's the bang when you pop a balloon. So that is a good assumption. The temperature, I will say that the temperature of the environment is equal to 275 Kelvin, and that the temperature of the parcel is a little higher, it's 277 Kelvin. So let's calculate the mass density. The mass density of the environment is equal to the pressure divided by the gas constant from air, which is 287, times the temperature, which is 275, and that is 1.014. Let's also do that for the parcel. It's the same calculation, just as another temperature, and that gives 1.006. And of course, if the mass density is kilogram per meter cubed in both places. All right. Let's just calculate the let's use this first. So what can we say? Well, for the environment, we have the volume. It's the same. We have the mass density of the environment times gravity, and the force of gravity. Here it comes. We need the force of gravity. It gives us again the volume times the mass density of the parcel times gravity. Now we could actually calculate these values specifically, but since the volume and gravity is the same, we can just make them one. We can take them out, and then we can see that the force, I'll just put it in here, it's 1.014 and 1.006. Unfortunately, there was no more room left on my memory card, and so some of the explanation got lost. What I was going to say was that, as you can see from the two numbers, rho e equals 1.034 and rho p equals 1.006, and given that v and g are the same for both cases, the upward force given by v times rho e times g is greater than the downward force on the parcel, v times rho p times g. The parcel moves upwards. You can also relate this easily to balloons. You just have to add the weight, the downward force, to the downward force on the parcel. This would be F total equals Fp plus Fb, where Fb is the force from the basket under the balloon with the people inside. As you also can imagine now, you will then need to increase the temperature of the air inside the balloon in order to create an upward force greater than the downward force. In the part of the video you can see next, I will have calculated the pressure from the equation P equals rho times R times T, where you can see that the pressure is also different. You can, however, not use this as an argument to dismiss gravity. But remember, without any gravity, we wouldn't have a pressure at all, because the pressure increases because of gravity, due to gravity. Alright? The last thing I want to discuss is how our atmosphere is built up. And I'm going to do that, well, I'm going to erase the board and then put up some new stuff on there. Alright. So this is sort of a rough representation on how the temperature varies in the atmosphere. Out along here, the y-axis, we have the height in kilometers, 10, 50 and 90, and then upwards. Here we have the temperature in Kelvin, so at the surface of the Earth we have roughly 288 Kelvin, and in the Stratosphere we have roughly 200 Kelvin. Alright, so let's try to explain why it is that we see these temperature differences. I think that is one of the things that Brian Mullen, I really hope that he sees this video, he struggles a little bit. Especially, how can the thermosphere be said to be very warm when we actually can measure the temperature? And like I said before, at one of the first parts of this video, in relation to the ideal gas law, is that we have a definition, we have a relationship between the velocity of the particles and their temperature. So without putting a thermometer in the thermosphere, we can actually say something about the temperature anyway, and actually this had to continue up like this, but my whiteboard is too small. We can say something about how the relative temperature of the particles in the thermosphere is, because we can calculate or find their velocity. Alright, but let's look at why we have this strange variation in the temperature. In most other planets in the solar system, it would look more like this. So it would decrease and then increase again. But we have sort of a strange relationship. Let's first name them. Where we live, and 10 kilometers and below, we have the troposphere. Tropos is I think it's a Greek word for moving around, and that is because the Earth gets radiated by the sun. It is warmer at the surface than it is up here, as you can see, and this creates convection, where the particles, the air particles, moves around. You can show that very simply. Take a pot, put some water in, put it on a stove, and turn on the heat. You would see that the water begins to distribute the temperature from the bottom up to the top by convection. Alright. From there, when we go over to we have the stratosphere here in between 10 and 50 kilometers. We have the mesosphere between 50 and 90 kilometers. And we have the thermosphere from 90 kilometers and above. And in between we have the tropopause, the stratopause, and the mesopause, and of course we don't have a thermopause because it just goes all the way out to where there are no particles whatsoever. So, in order to understand how this temperature variation can be, we need to look at how the sun is radiating our Earth. So, if we take a plot where we take intensity or energy compared to wavelength, it would look something like this, where this area here is visible, this area here is infrared, and this area here is ultraviolet, and down here we have higher energy like gamma, X-ray, and so on. Also high energy particles. And we can sort of, if we have to put it in, we can say that we have visible here, then we have near infrared, mid infrared, and far infrared. Likewise, we have near ultraviolet, mid ultraviolet, and far ultraviolet. And that is how we can put this, divide this into smaller parts. So, the thermosphere contains particles that absorb high energy particles, X-ray, gamma, and far ultraviolet. The stratosphere here absorbs mid ultraviolet and near ultraviolet, and anything from visible and infrared will to some degree extend down to the surface and heat up the crust of the Earth. So, how can we explain this temperature variation? Well, in the thermosphere, the particles will absorb the energy from all these particles. So of course, the temperature will increase as we go out, because as we go further down, there will be more and more particles, and so there will be more and more particles to absorb it, and so they will protect each other, you can say it like that. Then we have the mesopause, where the temperature no, let's take it from the bottom up. At the surface of the Earth, the temperature is higher because the visible light and the infrared light hits the surface of the Earth, warms it up, and then the Earth will begin to radiate and heat up the particles nearest the surface, and then because of convection they will sort of blend each other, but it will still be warmer closer to the surface. Of course, then the temperature will decrease until we get to the stratosphere. We have the tropospause where the temperature is lowest. Then we get to the stratosphere, which contains high amount of ozone. And ozone absorbs mid and near ultraviolet particles, or radiation. So of course, because it absorbs these particles, they are also high energy particles. Ultraviolet light is high energy. The temperature will increase, and of course, because the light comes out from this side here down, then the temperature will be highest here, because these are the particles, the ozone particles that are closest and will take the most of it, of the light, and then it will gradually decrease until we get down to the tropopause. Then we have the stratopause, where the temperature is highest, and in the mesosphere, which actually means the mid part, the temperature will again begin to decrease, because there are no real particles here absorbing anything. But when we get to the mesopause, we have the particles in the thermosphere, which absorbs the high energy particles, the X-rays, the gamma rays, and the far infrared, which are also very high energy particles and high energy light. And they will, again, because the light comes down from the top, the particles at the edge, if we can call it that, of the thermosphere, will take most of the radiation, absorb most of the radiation, and then it will gradually decrease downwards until we get to the mesopause. And this explains why we have, from the surface of the Earth, a decrease in temperature, because it is the Earth that absorbs the light. Atmosphere, Earth, let's say surface. So, surface, sorry, that's not very good written. Surface. So all light from here and to lower wavelength will be absorbed in the atmosphere, and all the light from the visible, start of the visible spectrum, and then upwards to higher wavelength, a greater wavelength, will be absorbed mostly by the Earth. Now there are clouds and sort of things that will also absorb some of the infrared radiation. That's also because clouds can reflect infrared radiation. But basically, this is how it works. So this explains why the troposphere at the surface of the Earth is very warm. It's where most of the light hits and warms up the surface. As we go up in the atmosphere until we get to the tropopause, the temperature will decrease, because there are more particles from the Earth and up to absorb and reflect the radiation from the Earth. But from the tropopause and then in the stratosphere up to the stratopause, in the stratosphere, we will absorb mid-ultraviolet and near-ultraviolet. And of course, because the radiation comes down, let's put it here, radiation from Earth and radiation from Sun. Because the radiation from the Sun with the high energy particles, mid-ultraviolet and near-ultraviolet light, comes from the top, the temperature will be highest closest to the stratopause and then decrease down to the tropopause. And the same goes for the thermosphere, because all the high energy particles and the far infrared light comes from the sun outwards and in towards the Earth, the temperature will be highest at the edge of the thermosphere and then decrease gradually until we get down to the Mesopause. Now actually, just a small note, that is that at night time and daytime, the temperature of the thermosphere actually varies, and that makes perfectly sense. When the thermosphere is the part of the Earth with the thermosphere is pointing towards the sun, it gets radiation. When it's pointing away from the sun or it's nighttime, then it will not get any radiation. Now these temperatures has been measured by satellites, by weather balloons and so on. So these are numbers that we know pretty well. Thank you for listening. I hope that this video has given some more insights into why the Earth looked like it does and why the flat Earth, not theory, but claims like there is no need for gravity and so on, not quite truly holds. Until next time, bye.